Hi again, this is Xiong-Fei here to talk about MATHLAB, and the focus of this video will be on the algorithmic complexity and how the code works for MATHLAB. So for example, in our 3D mode, what we can do is that we can graph any sort of function, and what this is going to do, the code is going to do, is that it is going to loop through the x's, and it's going to loop through the y's, and it's going to generate a set of points along the domain along discrete intervals of the domain. And then after it has those points, it's going to connect those points going in one direction, then going in the other direction, until we have this graph that we see here. And what we do is, what we first have to do though is that we have to go to each and every point on these discrete intervals on our domain, and then evaluate the function at that point. And this is going to produce a vector. Now we're going to have a set of vectors that we're going to put in a two-dimensional array that we're going to draw, and what we are going to do with that two-dimensional array is that for every vector, we're going to project that vector, which is a three-dimensional vector, onto this two-dimensional plane. Now the trick part of doing that is, how do we project a three-dimensional vector onto a two-dimensional plane such that the image still looks three-dimensional? And that is something that took up a lot of my time when I started coding MATHLAB. And the same thing goes for any of these other coordinates. For example, in spherical, what you're going to do is that you're going to loop through the thetas, you're going to loop through the phis, and you're still going to produce that set of vectors that you're going to use to project onto the screen. And the same thing goes for two-dimensional graphics. What we're going to do is that we're going to loop through the x's, and we're going to generate a set of two-dimensional vectors this time that we're going to map to this canvas when we draw it. And the same thing for any other coordinate system. For example, I just said that we have cosine of theta times 5 minus 3 or something like that. We're going to loop through the thetas here. We're going to have a set of 2D vectors that we're going to project onto this domain and connect them. Now, let's go head on to some other features in MATLAB here. Now, for example, in a differential equations mode, for example, let's just say that we want to draw a function, for example, at negative y over x or something like that, and then we specify an initial condition, for example, 2, 3 here. And what it's going to do is that first it's going to take a look at this at our differential equation. And what it's going to do is that it's going to loop through the x's, and it's going to loop through the y's on this domain of the graph here, and it's going to produce these small little tick marks from using the derivative at that point that is specified by this differential equation. And then what it's going to do is that it's going to look at our initial value, which is 2, 3 here. And what it's going to do is that it's going to start at 2, 3, and it's going to make very small steps in the positive x direction and in the negative x direction to and generate a set of vectors, vectors, this time two-dimensional, onto the into an array, and then we're going to connect those vectors by drawing very small lines. And this method of solving an initial value problem is actually called Euler's method. And for more advanced mathematical software that uses numerical methods, you might see the Runge-Kutta method, which often goes up to RK3 or RK4 to solve these initial value problems that we see here. However, if in the case of MATLAB, we're just using Euler's method, which uses linear approximation and use it in very small steps. So now we're going to skip over the calculator part. We're going to head to this statistics mode. And what we're going to see is that we're going to put in values, for example, -1, say cosine of 0, and 4 times 4 divided by 5, and 7 plus 8 or something, or 6 for that matter. And then we can graph our points here. So that's 3, and we're going to have this be around what, say 50 for that matter. And then if we're using the linear regression tool, we can again draw our linear regression line. And what linear regression does is that it just takes the aggregate statistics of the x and the y's, and then it finds a line of best fit using those equations. Now, for these aggregate statistics, there are formulas for each and every one of these statistics that are pretty straightforward. That's kind of unnecessary for me to go over. As for confidence intervals, there are equations that we use. For z intervals, we use the normal distribution, and for t intervals, we use the student's t distribution in order to find t values that we can use equations for and map a confidence interval within a certain confidence, a certain degree of confidence. And that's all for these, and I hope that you guys stay tuned for my other video in which I'll explain the algorithmic complexity of various functions within the calculator mode. And thank you.